The information given in this problem is related to a test for HIV. We can assume that the table here summarizes the results of the test for a group that contains people that we know have the virus and people that we know do not have the virus. If the antibodies are present, then for simplicity we are just going to call this D for disease. And if the antibodies are absent, we can assume that the person does not have the virus. And again, for simplicity, we're going to call this event ND for no disease. The first row of the table is related to people that we know have the virus, which means they have the disease. And it gives us probabilities of the test showing positive or the test showing negative. So let's first write down the probabilities that we have from the first row. So let's look at 0.9985. So that's our first probability. It's the probability that someone shows positive and we know that they have the disease. So the probability of showing positive knowing that someone has the disease is equal to 0.9985. So if someone has the disease, there are only two possibilities. They either show positive or they show negative. So the other possibility is probability that someone shows negative knowing that they have the disease, and that is equal to 0.0015. So when we add these two probabilities, it adds up to 1. That's what tells us that there are only two possibilities. So let's look at the next row, that is no disease. So the second row gives us the probabilities that the test will show either positive or negative. So the first number, 0.0060, that is the probability that the test will show positive when we know that the person does not have the virus. The second number in the second row is the probability that the test shows negative knowing that the person does not have the disease. And that is 0.9940. Since there are only two possibilities, when someone does not have the disease, the test will either show positive or negative. So these two probabilities add up to 1. So in any of these problems, these four probabilities will be given to you in some form. Now, in addition to that, when you read the next sentence, it says that 1% of a large population carries the antibodies to HIV. So that gives us the probability that a randomly chosen person from the large population actually has the disease, and that is equal to 1%, and 1% is 0.01. Now the only other possibility is that the person randomly selected does not have the disease, and that is equal to 1 minus the probability that the person has the disease, so that is equal to 1 minus 0.01, which is equal to 0.99. Let's say we select a person from the population. This person either has the disease or does not have the disease. These are the only two possibilities. Let's put the probability that someone has the disease on this branch of the tree diagram, and the probability that someone does not have the disease on this branch of the tree diagram. Now, let's say the person who has the disease goes in for the test. There are two possibilities from that point on. The person can show positive on the test or show negative for the disease on the test. So let's put down the probabilities on these branches. So we know that someone has the disease, and now they've gone in for a test. So the probability that they'll show positive is 0.9985. Now, the other possibility is that the person with the disease, someone we know has the disease, might show negative on the test. So that would be with a probability of 0.0015. Now let's say a person does not have the disease, we know that. They go in for the test. Again, there are two possibilities. They can either show positive or they show negative. So let's put down the probabilities on these branches. So once we know that someone does not have the disease, the probability that they'll show positive is low 0.0060. Now the person without the disease, that is, goes in for the test. What's the probability that they will show negative? And that is equal to 0.9940. Now suppose we want to find the probability that someone has the disease and shows positive. We can use the tree diagram. All we have to do is go down this branch. So the probability that someone has the disease and shows positive is equal to, so the first step is they have the disease. So that would be with probability 0.01, and the probability that they show positive given that they have the disease, and that would be 0.9985. Now if we had to find the probability that someone has the disease and shows positive in a more formal way, that is using the multiplication rule, we would first have to decide whether the two events, having the disease and showing positive, are independent or not. So if the two events are independent, then we use the rule of multiplication, which is probability of A and B is probability of A times the probability of B. If the two events are not independent, then we have to use the other rule, multiplication rule, and that is probability of A and B is probability of A times the probability of the second event B, but then we have to consider that the first event happened. So probability of A times the probability of B given A. Now the probability that a randomly chosen person will show positive on the test will depend on whether the person has the disease or not. So the two events clearly are not independent of each other. So that tells us that the rule that we apply to this situation is the multiplication rule that is highlighted here. So the rule we're going to use is probability of D and positive is probability of the first event, which is probability of D, times the probability that the randomly chosen person shows positive, knowing that the person has the disease. So the multiplication rule gives us exactly the same result as expected. Probability of having the disease is 0.01 times probability of positive given disease is 0.9985. In the next question, we need to figure out the probability that the test will show positive. So, randomly chosen person, what is the probability that the test will show positive? So, what we need to figure out is P of the probability of a randomly chosen person showing positive. To figure out this probability that someone shows positive, we need to think of two possibilities. It is possible that the person has the disease and shows positive, or it is also possible that the person does not have the disease and still shows positive. So that is equal to probability that someone has the disease and shows positive, or, so we are using the addition rule for disjoint events, probability that someone does not have the disease and shows positive. Now we have to figure out the probability that someone has the disease and shows positive. So the word here is and. So we use the multiplication rule for two events that are not independent of each other. So that is equal to, so probability of disease and positive is equal to probability of disease times the probability of positive given that the person has the disease, plus the probability of no disease and positive is the probability of the first event, no disease, times, because it's a multiplication rule, probability of the second event given that, because of the fact that the two events are not independent of each other, we do have to consider that the person does not have the disease. Now all we have to do is plug in the probabilities. So we plug in the probabilities. So it's 0.01 times 0.9985 plus 0.99 times 0.0060. And that is equal to 0.015925, which is approximately equal to 1.59%. So if you recall, probability that someone has the disease is equal to 1%, and the probability that someone shows positive, we just determined, is equal to 1.59%. Now, does it make sense that a slightly larger percent of the people will show positive? So there's only 1% that actually has the disease, but 1.59% of the people will show positive, because we know the test is not always correct.